Okay, today we're going to discuss briefly how we can address potential model violations. So last time we talked about using the residuals of a fitted regression model to help us give us an idea through various plots whether the basic assumptions of multiple linear regression are satisfied or whether they are perhaps violated. So of course, I should mention that the plots don't provide a foolproof way of assessing all of those assumptions, but they do give us some idea of whether our model is valid and with it the associated inference. Okay, so today we're going to talk about some strategies we can use to address some potential violations of the regression model assumptions. Some potential violations of model assumptions. Okay, and the key point of the residual plots is they give us some idea of whether there is a good chance that there is a problem with the model, and so let's talk about some ways we could address some of those concerns. So, if the residual plots reveal problems, with the assumptions, and I would also note here that we can't test all the assumptions perfectly with the plots, although the plots don't fully help us test things like check, I should say. Things like linearity, the correctness of the linear relationship, and independence of all the errors. Okay, so we can only do that to some extent. One, because especially when you have many variables, it can be hard to check linearity. And secondly, independence is very hard to check. We can only look at certain aspects of it. So we use, for example, the plot of the residuals versus the fitted values. We also can look at whether there's any time dependence in the residuals. So those are various aspects of independence, but the ideal case of independence, which we often assume is notoriously hard to indeed verify. So what the plots do is, if there are egregious violations, hopefully we can see that in some of the plots. Okay, and so, all right, so if we do see problems with the model assumptions, there's a few strategies I want to outline today for what we could do about it. Okay, so we might we have a few strategies that we might use. We might be able to solve or address some of these issues. Okay, so I'm going to talk about a few basic strategies. I'll go into the first one in a little more detail, which is transformations. Okay, we could also create new variables and add to the model. Adding variables to the model, and as an extension of the framework we're talking about, you could also use different error distributions. So in other words, to leave behind the normal and maybe use a different error structure on the residuals. Okay, so I'm going to focus on transformations first, because they are quite helpful in solving some common issues, especially when the variance of the response is not constant over overall values of the predictors. Okay, so let's dive into this. So first one is transformations, especially of the response. We'll talk about transformation of the response first, and they're often done to stabilize the variance. So these are known as variance stabilizing transformations. Okay, so on the response. Okay, so we have the yi's. We can apply a transformation on them to solve non-constant variance. Okay, can help. Non-constant variance, and often this is revealed by the residual plot of residuals versus fitted values. Okay, identified in the residuals versus the fitted values plots. Okay, so the key idea is we apply a function and we transform the data before fitting the regression model. Okay, so apply a function, let's call it g, and then fit regression on the transformed data. So g yi. Okay, so in other words, we will fit this regression. So we have g yi. And so this is when we fit the usual multiple linear regression. Okay, the reason I write this out is once we do a transformation, we realize that it can drastically change the scale of the response. And so compared to fitting yi on the predictors, GYI could have a very different look in terms of the residuals, because the transformation can change the scale of the response. Okay, so by writing it out, we notice that, well, we're not changing anything on the right side, so therefore the residual term is going to also change with the transformation. Okay, so we have to be careful in how we interpret the residual. So note that this can have a big change, can drastically change the sum of squares of residual, because y is now transformed, and so along with that, the estimate of the residual variance. Okay, so we cannot use those. Cannot directly compare these. Among different transformations. depending on what we choose for the function g. For example, we take the log of the data. Well, of course, that's going to we're now going to be measuring error on the log scale, and so that's of course going to give us a very different scale in the residuals. Okay, so that's the key idea of doing transformation to stabilize variance. Okay, okay. So why is this a rational thing to do? Well, let's give some intuition, and then we will dig into how it actually works. Okay, so first a quick rationale for why this is often a good solution to non-constant variance. So rationale for doing this. So the variance of the response often, as we gave you in the example plots last lecture, and also in the example I showed you with the Florida oranges, as the county gets larger, the variance in the amount of oranges produced also gets bigger. Okay, so the variance, so that's a common thing we see. So the variance of response could be a function of the expected value of the response. Okay, so so the variance of the response might be a function of the means. Okay, so we've called that mu I, which is the expectation of the expectation of response. Okay. Okay, so for example, larger means larger response. Yeah, so larger responses and mean response. I'll just say mean responses. Larger mu I might have having larger variances. Okay, so an example of that is the Florida oranges. Okay, and so if that's the case, then we could perhaps write the variance as a function of the mean. Okay, so we could write variance yi. Okay, well remember yi is all this regression part plus the error, so it's really just boils down to the variance of the error. Okay, so that's where the same error variance across all values of the predictors. That's where that assumption comes into play. Okay, and so if it's a function of the mean, so this could look like some function h mu I times sigma squared. Okay, so it could be, so we could say could be expressed in this form. Okay, so rather than having a constant variance, we might be able to explain the variance as a function of the mean. Okay, so that's what this function h here is doing for some function h, which is of course positive because the variance has to be positive. Okay, so the variance could be related to the mean in some form like this, and this is specifically the case where applying a transformation on yi can actually help to solve this problem. Okay, and so if we can express the variance in this form, then we want to find the transformation g. Okay, so this is some variance maybe increases with the response. So what we can do then is we transform y to account for this term and basically cancel it out. Okay, so that's our strategy. So in which case we we want the variance after transformation. So variance after transformation to G yi. Okay, so we want after transformation to be approximately constant. In other words, to cancel out this effect of the mean. Okay, so all right, so that's the idea here. Okay, so how we're going to do this is we're going to do a quick linearization. So we're going to do a quick Taylor expansion on G of yi. So based on the first order, we can do a linearized approximation to get rid of this function of the mean response, h. Okay, so let's do it. We do a first order Taylor expansion. Okay, so on G of yi. Okay, so we're going to expand it around the expected response, so mu I. So we're going to have, well, G of mu I. And then we'll have the difference, yi minus mu I. And first derivative, G prime mu I. Okay, and, well, this, of course, we're ignoring the higher order terms. That's why I'm calling this first order expansion. Okay, so let's take the variance of this. So we take variance GYI. So what happens to the, in other words, based on the first term Taylor expansion, what happens to the variance of the transformed response? So after I apply G on the response, what's going to happen to the resulting variance? As we noted, the transformation is going to change the variance. Now we're going to look at, well, approximately how much does it change the variance. Okay, so that means we're going to take the variance of the right-hand side. And you notice all of this stuff is constant, right? G of mu I is constant. So all of these are just constant terms. So the only random variable is the yi in there. Okay, so this stuff in green is constants. So the only random variable is this, is the yi. Okay, and so variance of constants added don't do anything, and then once you expand this, the variance of this constant doesn't do anything. So really all that's left is you have variance of G prime mu I times yi. And so based on this expansion, we simply have the constant squared. So you have G prime mu I squared, and then variance yi. Okay, and so when the variance can be expressed like this, then we notice that when we have this case, then now we know what G. Now we have a relationship between the G prime mu I squared term and H mu I. In fact, these two have to cancel out. At least everything involving mu I has to cancel out, and it has. So in other words, G prime mu I squared must be proportional, at least up to a multiplicative constant that doesn't involve the mean, with H mu I. Okay, so therefore, let's write down what I just said. Therefore, thus, for variance variance GYI to be constant. So we need these two things to cancel out up to a multiplicative constant. So we need g so we need g prime mu I squared to be at least up to a constant proportionality, having canceling out this structure, so it needs to be 1 over h mu I. Okay, so you haven't seen this symbol this symbol before. This is the proportional to sign. Okay, so we can calculate this, so if based on the data we have a sense of what h is, then we can find the appropriate transformation based on this relationship. All right, so that's the basic idea. So now let's look at some examples of that. Okay, so examples. Okay, and so let's look at a few examples of h first. Okay, so number one. So what should we do when h mu, for instance, when h of mu I is mu I? Okay, so first, well, what does that mean? So that it says, so if the function h is mu I, then that means variance y is sigma squared times mu I. Okay, so in other words, the variance is proportional to the mean. So in words, okay, so let's write that down. So variance of mu yi is some constant sigma squared times mu I, and if we drop the sigma squared, in other words, conceptually, it is proportional to the mean. Okay, so this case might be relevant to for example, the Florida orange example we saw, where it did appear the variance grew with the mean. Okay, so just to illustrate this idea, so let's write this in words first. So the variance in responses is proportional to the mean response. Okay, so in this case, well, what would be the right transformation g on the responses to deal with this type of non-constant variance? Okay, so according to this expression, we want g prime of mu I squared to be proportional to 1 over h mu I. Okay, so let's write that. So in this case, need. Okay, so let's take the square root. So g prime mu I to be proportional to 1 over the square root of h mu I, and h mu I is mu I. So let's plug that in. 1 over root mu I. Okay, and so now we just need to remember a little bit of calculus. So what kind of function, after taking the derivative, will give us a 1 over square root of it? Well, therefore we recognize that g should be a square root function. Okay, so therefore we want to apply. So therefore, g of mu I equals, for example, just take root mu I will satisfy this expression. Okay, so this derivative is 1 over 2 root mu I, which is proportional to 1 over root mu I, and therefore it accomplishes what we need, such that these terms cancel out and just leave us with a constant. Okay, so therefore we apply works, and we apply the transformation g yi. So take all the responses, and you can take the square root of all of them, and then you fit the regression model using square root yi as the response to obtain approximately constant variance. Okay, so that should help stabilize the variance if that is the in the case where the variance is proportional to the mean response. Okay, so let's look at a couple more. So I alluded to the fact that sometimes we might take log transformations. Okay, so let's next see when the log transformation is appropriate. Okay, so that's first example. Second example is when h mu I equal to mu I squared. Okay, so so in this case, the variance is growing quadratically in the mean, whereas in this case, it's growing linearly. So now, in this case, that means the variance of the response is mu I squared times sigma squared, or in other words, proportional to the squared expected response. Well, remember that square root of the variance is standard deviations, or equivalently. So why this one is also intuitive is because it means the standard deviation of yi is proportional to mu I. Okay, so therefore with a square in words, then the variance in the response, I should now say the standard deviation in the response. So standard deviation of the response is now proportional to the mean response. Okay, so this is also commonly encountered. So in both cases, the variance, you will see that the variances in the errors increases with the fitted value. But to what extent it increases, well, it could grow proportional to the variance, or it could grow faster, being proportional to the standard deviation. Okay, so what's the correct transformation here? So let's go through this process again. So now we need g prime mu I to be proportional to 1. Okay, so we again 1 over the square root of h. Okay, so 1 over mu I. Okay, and so now we have this relationship, and again from our first calculus course, well, what functional form will give us derivative that looks like 1 over mu I? Well, this is in fact a log transform. Okay, so so g, setting g to be the log mu I works. And whenever I write log, I mean natural log. Okay, so that's just to be clear. Whenever I write log, I mean you can also call it ln. Okay, and so we apply, the transformation g yi equals the natural log of yi. Okay, and so in this case, the log transformation stabilizes the variance. Okay, and so those are two special cases of transforms, and in particular transforms that can be expressed as within the broader class of what we call power transforms. Okay, and so the broader family of transformations that these are part of, so like the square root transformation and log transformation, can be expressed as special cases of this what's known as the Box-Cox transformation, which is the family of all transformations that can be expressed as a power. Okay, so the transformations GYI of the form yi to the lambda minus 1 over lambda for lambda not equal to 0, and log yi or lambda equal to 0. Okay, is okay. So this captures all transformations of the form where you apply a power on the response. Okay, it's the class of power transforms. Okay, and in the context of linear models and statistics, the two guys, Box and Cox, well-known statisticians, suggested this as a way to handle more generally non-constant variance, which is due to which can be fixed by applying a power. Okay, so Box-Cox transformation, and we can use likelihood methods to find the optimal value of lambda. Okay, so some specific examples are to take, for example, if you take a square root transformation, that's applying lambda equals a half. And between the log transformation, but according to this definition, it's lambda equals 0. So you can also do, if for example you do the reciprocal, like 1 over y. Well, that's also covered by this class of transform. Okay, in that case, lambda will be minus 1, for instance. Okay, but let me first explain why that works. What is g prime of mu I in this case? Okay, so if I apply the function on the mean, and then I take its derivative, because that's the relationship we found earlier with h. Okay, so I take the derivative of mu I. Notice that by design, this lambda part is going to cancel, so you're going to have I, the lambda minus 1, okay, if for any lambda not equal to 0, and then you're going to have 1 over, I'm writing in terms of mu I, so in terms of the mean, so mu I, the lambda minus 1, and then 1 over mu I for lambda equal 0. Okay, and so if that's the form of g prime, what kind of non-constant variance can this address? So what's the corresponding function h on the mean? Okay, so h mu I. Okay, so h mu I as from our earlier relationship. So okay, so I didn't. It's gone now, but remember we had g prime of mu I squared proportional to 1 over h mu I. Okay, and so h mu I then, okay, well, you just flip this around, so it addresses any transformations of the form, okay, so 1 over, take the reciprocal of this, so what you see then is it deals with any type of, okay, so 1 over I squared. So basically this addresses any non-constant variance of the form. So lambda can be any positive or negative real number in this expression. So it addresses any variance of the form where you have the mean to any arbitrary power. Okay, so that gives us the rationale for this kind of transformation. Okay, so the Box-Cox transformation is able to address, can handle, help address non-constant variance of the form ui to some power times sigma squared. Okay, so if the variance of the response is proportional to the mean to some arbitrary power, then this transformation can help fix that. Is there any restriction on C? Well, I mean, no, because lambda is defined. Well, I didn't write out both cases here, but from this expression, lambda can be you can plug in any real number for lambda. So the only part where this is not defined is when lambda equals 0. So we define the special case that basically this is taking the limit. So then we treat lambda equals 0 as the log. So this can deal with any power in the transformation. So that includes, for example, the special cases. So special cases include so if lambda equals a half, is the square root transformation. Lambda equals 0 is defined as the log transformation. Well, if you don't do anything, well then that's just the identity is okay, you don't transform, and you can even put in negative values. So you can do, for example, lambda equals -1 as the reciprocal. Okay, so, well, given you could potentially plug in any type of power transform, well, how do you find the best one? Well, we can automatically do that by fitting a variety of lambdas and find the one that works the best according to a criteria like the likelihood function. Okay, so the function in R, for example, can automatically test various sequence, try a sequence of different lambdas and find the one with the best likelihood. Try a sequence of lambda and find choice that gives the best value of the likelihood. Okay, I should point out though that after transforming the responses, that's also going to affect the interpretation of our parameters beta. Okay, so the first, when I rewrote the regression equation after transformation, notice that the beta now corresponds to corresponds to change in g of y. Okay, so that's going to throw off some of our usual interpretations. Okay, so let's make that point before moving on. Okay, so note that interpreting our parameter estimate, so the beta j hats, can be less intuitive as a result of the transformation. As a result of transformation. Okay, so why is that? Well, since now increasing, so if we look at beta hat j, for instance, now increasing the corresponding xj by 1 unit, corresponds to change of estimated change, and estimated change of beta hat j. Okay, but that's not in the mean response anymore. It's now in the transformed response. Okay, so okay, so I'll just write it in words, g of the response. Okay, so it's not as nice to interpret, because, for example, we took the square roots. We now beta j corresponds to a change in the amount of change in the square root of the response. And especially if we were to do the Box-Cox transformation, and we find, for example, lambda equals 0.31415, and some very odd number like that, for instance, then it's hard to interpret what that power actually means. In the case of square root, at least we get it's easier to have a handle on that. But for arbitrary lambdas, the interpretation we lose out on having nice interpretations, especially when lambda is some arbitrary number. Now, in one special case, at least, the interpretation is quite intuitive, and that's the log. Okay, so can be less intuitive. Okay, but for the log transform, so we take the natural log of all the responses, though, we do have a nice interpretation. Okay, now the beta hat j, represents expected estimate of expected change. In the log scale. Okay, which is equivalent to a multiplicative change, right? Because if you have because of our log rule, so if you increase the log by this beta hat j units, that corresponds to a multiplicative change of e to the beta hat j. Okay. So that corresponds to which corresponds to okay, so it's you exponentiate the difference. Okay, so this is being actually I should be a little more precise here. This is the expected change in the response in the log scale. So let's just write it in words. On the log scale, okay, which corresponds to e to the beta hat j being the expected multiplicative change applied to the original to the response on the original scale. Okay, so log transforms are quite interpretable. We just have to think of it as now a change in x corresponds to a multiplicative change in y. Okay, so this one is so the log transform has a nice interpretation. But as we mentioned, for arbitrary lambdas, the transform might be less interpretable. Okay, so we didn't want to make that as a note of caution. So if it's important to have an interpretable model, then we might want to use values of lambda that are easily understood, like log or inverse or square root even. But of course, there's no guarantee of that. We just search for the one with the best likelihood. Okay, so that was the first key idea, which is we can transform the response to help address issues in non-constant variance. Right, okay, so there's a question, if we apply a transformation to y, would that violate our assumption of a linear relationship between y and x? So that will indeed change the nature of the relationship. So now, as based on the first equation we wrote down, clearly if we fit the regression on the transformed version of y, then we're now assuming that the x's are linearly related to g of y rather than y itself. Okay, and so while we fix the non-constant variance, we could potentially introduce other problems if the x's are no longer linear related to g of y. Okay, so that is a legitimate concern, and so we may want to, for example, check how the plots of the residuals versus the xj's after transforming y. So that would be another good plot to check as to whether this introduces other issues in the model, especially as pointed out whether a linear relationship is reasonable between x and the transformed version of the response. Which is an excellent segue into this next thing, which is the second notion of transformation. We can also apply transformation on the predictors. So sometimes that can be helpful. Okay, so this is the second point, is doing some things on the explanatory variables. Okay, so there are as a second strategy, and sometimes we might need to apply them together, and I'll show you that in R in terms of the Florida Orange example, where it might be helpful to transform both y and a predictor. Okay, so broadly, so for this strategy, I mainly just want to give an overview for now of some of the things that we can do. Okay, so the second strategy is transforming or adding explanatory variables. Okay, so why might we do that? Well, if y, or the transformed version of y, might not be the linear relation between x and y, or the transformed y, might not be appropriate. So if if y, or g of the response, has a clear nonlinear relation with some predictor xj. Okay, for example, revealed by the plot of residual versus predictor, or for example, as there's other ways to see this too. For example, you make the pairs plot, and even just when or the pairs plot, which is between all predictors and y, and y. Okay, so if the relationship appears to be nonlinear, we can consider transforming x as well. And so here are some basic strategies. Okay, so we can consider transforming xj. Okay, so we can apply similar kinds of transformations. We could take the log, square roots, etc. So power transformations could be relevant. Okay, so that's the first kind of point within this line of thought. Okay, so if there's apparent nonlinearity, we can transform the response. We could also consider adding terms. Okay, so an extension of linear regression is to look at use polynomial terms. Could add. Okay, and so that's subpoint number one. Subpoint number two could add polynomial terms. Okay, so you do like x squared, x cubed, and so on. And you can add those into the regression. Let me explain what I mean by that. So what's important to note here is you can create new variables like this, okay, as a general strategy. Of course, we want to be judicious about it and have it's good to have some basis based on the context of the problem for why this might be appropriate. But at least I want to explain, conceptually how we would do it, right? So, for example, okay, so this is continuing this thought. Okay, so we start with the model, for instance, y equals beta 0 plus beta 1, x I1 plus beta 2, x I2 plus epsilon I. Okay, and suppose we think adding a quadratic term say we want x1 squared, okay, is appropriate. Okay, so as conceptually, how would we do that? Well, we would simply define a new variable. Then we would define. Okay, so we'll define x3. Okay, so I'm going to take each x1. Okay, so I'm going to take xi1, I'm going to square it, and then I'm going to define this new variable. And fit. Okay, so now we have a regression with 3 variables. Okay, so now we have, this is a valid model to fit. Okay, so in this case, the third xi3, so x3 is defined in terms of x1, it's simply x1 squared, and you could throw that in as an additional predictor in the model. Okay, and that's so this is, so the reason I write this out is to point out that this is still linear, okay, because it's still linear in the, it's still a linear model because the parameters are linear, okay, and which is still linear in the parameters, so it's still considered a linear model in beta. Okay, so that's what we can see by writing it this way. Inference, you can still do inference because x and also note that x1, for instance, is linearly, is not, I should write not, and x1 squared aren't linearly dependent, so that's not going to be a problem either. So the question is, are we treating the polynomial term as a linear term? So the reason we can still call it linear is because the coefficient we're applying on x3 is the same as we would normally do for multiple linear regression. It's just sometimes known as polynomial regression because the way we constructed the predictor x3 is in terms of some existing predictor. Okay, but the resulting model is still considered under the framework of linear models because the betas we fit they're linear in the parameters. So I've written it this way to show that this is indeed still valid as a linear model. Okay, so it's allowed to we're allowed to define new predictors in terms of in terms of existing ones and then add them into the model. Okay, so that's something I wanted to mention along the lines of adding polynomial terms. The other thing I want to mention is sometimes it might be appropriate to add what we call interaction terms. So I also want to mention that briefly. So the third subpoint in these set of strategies is to add interaction terms. Okay, again, just want to give you a quick overview of how conceptually how we would do this. So what's interaction? So interaction between two variables is when, say you have xi and xj, okay? So xi, the two predictors xi and xj, we say they interact if the effect of xi on y depends on the value of xj. So that's called interaction. Okay, so if we think the effect of xi on the response, okay, so it depends on on the value of a different predictor, xj. Okay, so again, we start with this basic model. Okay, so suppose we think x1 and x2 interact, then we might fit okay, so we're going to write the model, so yi beta 0 equals beta 0 plus, so you have the two original predictors, i1, i2. So again, we could define a new variable and fit. Okay, so again, I can call it xi3, where xi3 is defined to be the product of xi1 times xi2. Okay, so again, there's we can throw in an additional explanatory variable. Okay, it's simply based on calculated from existing variables. In this case, to fit interaction, we could consider adding the product of two variables and adding that into the variable and fitting a linear model coefficient on that. Okay, and so why does this address interaction? Well, so that, okay, so I take yi and I rewrite it slightly differently. We'll see why we can think of this as interaction. So because xi3 is defined as this product, we can write equivalently beta 0, and then I can do, okay, so I'm going to factor out, I'm going to combine these two terms. Okay, so I have xi1 here. Okay, so we'll have beta 1 plus, okay, beta 3 xi2 times xi1. Okay, so if I group the terms that way, we can see more clearly what's going on. And beta 2 xi2 plus epsilon. Okay, so you notice that so this is equivalent. This is the same. These are the same model, but and this, of course, this form is the one we usually fit. But to see why this actually helps address what we call interaction, I can write it in this way. Okay, so these are the same. These are the same expressions. But what we see here is, okay, so the effect of xi1. It now depends on the value of xi2. Okay, so in other words, you can change, so one unit, the effect of a unit change in xi1 now also depends on the value of xi2. Okay, so that's why this addresses this question of whether there is what we call an interaction effect. Okay, so for example, if x2 was 0, then the effect of x1 is just beta 1. But if x2 was like 1, then we're now assuming the effect of x1 on the response is beta 1 plus beta 3. Okay, so therefore you see the effect of xi1 depends on the value of xi2. Okay, so the effect depends on xi2. Okay, because you see that in the expression here. Okay, so that's called interaction. Now, in practice, of course, there could be a lot of potential interactions, and so we want to be judicious about how many interactions we actually throw in the model, if any. Okay, so just as a side note, in general, there's Okay, so you could potentially have an interaction between any two variables. So let's P choose two possible interactions involving two variables. And in fact, I mean, you could go further and you could create like three-way interaction between x2 and x3 and so on, right? So this is just overviewing the kind of extensions that this allows us to do in our model. So there are a lot of possible interactions. So we should carefully consider, which is a lot. So consider whether interactions are conceptually plausible. One example I used in Stat 332 was diet and exercise, right? So the amount of exercise someone does and the amount of food they eat, and whether those two interact, right? So, for example, does the effect of diet also improve with the amount of exercise you do? If it does, then that would be an example of two interacting predictors. Okay, so often for interactions, if we want to consider putting them in the model, we should ask ourselves whether that seems a conceptually reasonable thing to do, especially when there's a lot of predictors. We can't generally, often we cannot consider all the possible interactions. Okay, so I've overviewed a few different strategies of things we might do to deal with nonlinearity between the response and the predictors. Okay, so we talked about transforming individual predictors, and then broadly speaking, there's also these extensions to the multiple linear regression model where we could throw in polynomial terms, we could add interaction terms. So at least I want you to have an overview of the kind of things we can do. Finally, get to the last strategy, and then I'll show you a quick R demo, is the errors. Okay, so last time we talked about quantile plots, also known as the QQ plot. So after we do all this analysis, it might be that we still have non-normal errors. Okay, so the QQ plot of residuals still not normal, So remember, normally distributed residuals will roughly follow the 45-degree line on the QQ plot. Okay, so suppose even transformations don't fix that. Okay, so even after any appropriate transformations. Okay, and so, well, this is the case where, not all errors are going to be normally distributed. I mean, it provides the basic framework where which has been the basis of our estimates and our hypothesis testing and our confidence intervals and all that. So all the things we've done are based on the normal distribution, but of course, in practice, by no means is the normal distribution always appropriate in terms of describing the deviations from the regression. From the regression line. Okay, and so if indeed the residuals are not normal, then you can consider using a different error distribution on the unexplained variability. Okay, so you can consider using different distribution for error term epsilon. Okay, and so, for example, we saw, if the errors are heavy-tailed, so there's more, the residuals are more spread out than compared to a normal. In other words, they're more heavy-tailed. We could consider using like some sort of a scaled t distribution, because a t distribution has heavier tails, for instance. And another example, use a t. Another example of a heavy-tailed distribution is a Cauchy. Okay, and then there are others, depending on what kind of distribution on the residuals seems to suggest. So I'll give you one more. So like Laplace, which is basically an exponential error, but with both positive and negative sides to it. And there are many others. Okay, but broadly speaking, just want to mention this as an extension to our regression framework, that it is possible to do regression and assume something else for the error term. But for our purposes, we're not gonna go there in our course. Okay, so those are the three strategies I outlined at the beginning of today, and so we talked about the transformations for stabilizing variance in a bit more detail than the others, and that's the one I want to illustrate for you in R to end off today. So I will be back with you on the computer in just a few moments, and we'll do that demo. Okay, so I have a quick demo on transformations, and we're going to use the same data that we looked at last time. So last time we looked at the Florida oranges data, and we noticed that the residuals didn't really satisfy the model assumptions. Okay, so I'm going to load that in again, and so we're going to fit the orange production for boxes to the number of acres. Okay, so last time we showed a plot of the residuals that it had a non-constant variance, so let's see it again here. So we noted last time that it appears the residuals have a higher variance for larger fitted values, which means that counties that are larger have also larger variance in the number of oranges produced, which makes sense. Okay, and so let's try a transformation. Okay, so remember this was the normal QQ plot, and we see that there's quite a bit of deviation in the tails. Okay, so based on what we learned today, let's try a log transformation on the response. Okay, so I'm going to fit the model using log of boxes as the response. Okay, so I can directly type that inside the LM formula, or alternatively, we can also, of course, also define a new variable by add a new variable to the data frame, which is the log as well. Okay, but this works, and look at the summary, and we'll notice that the R squared went down significantly. Okay, after a transform. Okay, so from like 93% to only 72%. Okay, so again, let's look at some diagnostic plots to see what's going on. So plot the fitted values based on this log transformed y on the residuals. And we notice that we now have what appears to be a different kind of issue. Okay, so before, if we go back a few plots, we had this problem where the variance increased a lot with the fitted values, and now we have what appears to be a different kind of problem. Now we see there's some sort of pattern, right, in the residuals. And this may not be, I mean, of course we don't want to jump to conclusion that it could be due to chance, but we could be careful here that there might be some sort of a pattern. Okay, so let's see how the normality looks. And indeed, it is significantly better after applying a log transform. For the most part, the problems in the tails of the distribution, which were highly non-normal before, have been fixed by the transformation. But there might be some problem in terms of the relationship between x and y, like whether that is still linear. So this suggests we should take a closer look. So let's do that. I'm going to plot the log transformed y. Okay, and then I'm going to look at this relationship. I should plot x first, so I'll fix that. Okay, so plot the predictor against the transformed response, and we get this sort of plot. And I think just looking at this, it's more evident that indeed x and log y are not very linearly related. Okay, so it looks like this is a nonlinear curve. Okay, and so in this case, since there's just one variable, it's pretty easy to address. Well, as we learned, we can simply transform x as well. Okay, and so since we observed previously that acres and boxes is quite linear, so if we take the log on y, and in this case it sort of causes a problem in this plot that is not really linear anymore, well, evidently if we apply the same transformation to x in this case, that should correct for this problem. Okay, so let's do that. So I'm now going to plot log x versus log y. Okay, so this is now the resulting plot where both x and y have been logged. Okay, so now we're back to an approximately linear relationship. Okay, so that looks good. So let's fit the model with log y on log x. Okay, and let's look at the normality. Okay, so I mean it's not perfect, but it's not bad. You have a few underspread residuals in the right tail, but it's not egregiously bad, unlike the one we started with. And let's also look at the residuals versus the fitted values, and indeed this is now an example of a very nice residual plot that doesn't show any patterns and doesn't show any non-constant variance to any noticeable degree. Okay, so this at least verifies the assumption that the residuals and the fitted values are approximately independent, so that checks out okay after applying a log transform to both x and y. Okay, so that's how we can address the problems that we noted last time for the Florida orange example. Okay, I also want to do a quick demo on doing the Box-Cox transformation. So let's load up the Python data from a few classes ago, and we're going to manually code up the indicator for whether for male and female, like we did before. Okay, and based on our earlier analysis with multicollinearity, we found that a model with male or female, and then the mass of the Python and the Snout event length was fairly good in that regard, didn't have strong multicollinearity. So let's fit the same model we had before, and this was the results we had. So all three predictors appear to be significant. Okay, so let's do our residual plot versus fitted values, and again we see a similar kind of problem where the variances appears to increase with the fitted value. Okay, and then correspondingly, we can look at whether the residuals are normally distributed. So here's the QQ plot, and here is the line. And again, we see a similar kind of issue within the tails of the distribution, which significantly deviates from the normal. Okay, so let's try applying an automatic Box-Cox transformation rather than choosing our own transform, just so you can see how it works. So the Box-Cox transformation is included in the mass library, so we will load that up. And it's very simple to call. You simply apply Box-Cox, the command, on the fitted regression model. So I just put the fitted model in here, and save the results in some variable. And what it does is it plots the log likelihood as a function of the power transform, lambda. And so what we're looking here on this plot is we want, based on our logic, we want the lambda that corresponds to the highest likelihood or transformed log likelihood value here. So it looks like something around like 0.3 or thereabouts looks the best according to a log likelihood. Okay, and so the object includes a bunch of things like the value of lambdas it tried, as well as the value of the log likelihood for those lambda values. So it gives me two vectors, an x vector and a y vector. Okay, so what we need to do is, well, we need to find which one is has the highest log likelihood. Okay, so remember we can construct this command in steps. So what's the highest log likelihood? Well, it's minus 554. Okay, which element in the vector of log likelihoods is the highest? Well, it's the 60th. Okay, and so and finally, which is the value of lambda that corresponds to this maximum log likelihood? So we now extract that element from the lambda vector, which is labeled as x here. Okay, so now we pick out the 60th element from this vector of lambdas, and that will tell us what the ideal lambda was based on this transformation. Turns out it's about 0.38. Okay, so let's call that value of lambda, and now we're going to fit a new regression model using that transformation. So I'm going to apply the Box-Cox formula. So I'm going to take the response to the power lambda, minus 1, and divide by lambda. So now that I'm going to treat that as the Box-Cox transformed response, and then fit it to the same predictors. And we can look at the summary, and we can look at some of the residual plots. So that, as we can see, at least based on residual plots, much of the non-constant variance now appears to have been addressed by this transformation. We can also look at whether the linearity according to the residuals on the individual predictors looks okay. Okay, so it's not too bad. We can also look at the whether the residuals are now more normal. Okay, so that's the last series of plots. So we do a QQ norm. Okay, actually that looks quite a bit better, and we add the line. I mean, there's still some skew here in the bottom part of the plot, but to a much larger degree, the errors are more normally distributed after this transform. Okay, so there's still some skew, as I commented here, but it's better than the one we had prior to transformation. Of course, as we pointed out, well, what does the power 0.384 mean? Well, I mean that of course affects the interpretability of the results, and it's a trade-off, right? We get better adherence to the assumptions, but then it's harder to interpret, well, what is a change according to a transformation of power 0.383 means. Okay, so there is that weakness of applying this sort of transformation. We do lose a bit of the interpretability in the coefficients. But if we're mainly interested in, say, the getting good assumptions, and for example, using the model for prediction, well, then the interpretability wouldn't be as important of a concern. So with that, I think that's all I want to say today. So I'll pause for a few moments and see if there are any lingering questions that I'll answer before I log off. Okay, so I think that will wrap up today. So your next quiz will be released after midnight. So make sure you complete that in the next couple days, and I will see you back on stream on Monday.